Welcome back to Audio Library and a brand new deep dive. Today, we're embarking on an extraordinary journey, guided by one of the most brilliant minds in history.
That's right.
We're talking about the universe, its beginnings, its ends, and, well, pretty much everything in between.
Mm-hmm.
Our mission for this deep dive is to unpack the really profound ideas from Stephen Hawking's monumental work, A Brief History of Time.
Indeed. And this isn't just, any physics book. It's really a cultural phenomenon.
Oh, absolutely.
It tackled the biggest questions imaginable, but with this astonishing clarity, it reached millions of people who perhaps never thought they'd delve into theoretical physics.
Yeah, it made it accessible.
Exactly. What's crucial here is how accessible Hawking made these incredibly complex ideas. He invited, a global audience into the scientific quest for understanding. He truly made the cosmos a conversation piece.
Absolutely. And it wasn't just some niche success, was it?
Not at all.
Hawking himself famously remarked, and I love this quote, that he sold more books on physics than Madonna has on sex.
That's quite something.
It really is. That's quite a statement. What truly captivates me, though, is how this book tapped into this universal curiosity.
Yeah.
Where did we come from?
Yeah.
And why is the universe the way it is?
Yes.
It speaks to something really fundamental within us, that urge to comprehend our place in the cosmos.
Our deep dive today will trace humanity's evolving understanding of the cosmos. We'll go from ancient beliefs all the way to the cutting-edge theories of relativity, quantum mechanics, and, of course, the persistent quest for a unified theory.
The theory of everything.
That's the goal. We'll help you gain a concise, yet, I think, thorough understanding of concepts that truly reshape our perception of reality. We'll see how each scientific leap built upon the last, often overturning deeply held beliefs.
So get ready for some, mind-bending concepts and some surprising historical twists. Because this deep dive is going to challenge maybe everything you thought you knew about space, time, and your place in the universe. We're going to explore how we arrived at our current scientific understanding, and importantly, what profound mysteries still remain. When we start thinking about the universe, it's easy to get lost in the sheer scale of it all, just mind-boggling.
It really is.
But for centuries, our understanding was far more grounded, quite literally. Stephen Hawking loved to open with that classic anecdote, didn't he? The little old lady who insisted the world was flat and resting on the back of a giant tortoise.
Right, the tortoise story.
And when asked what the tortoise stood on, she just declared, "It's turtles all the way down."
Huh, yes. It's a humorous way to highlight how deeply ingrained some early cosmological models were. And, how easily we can fall back on these kinds of infinite regressions when we don't have a coherent scientific explanation.
It really underscores the human need for an explanation, doesn't it? Any explanation sometimes.
Any explanation, exactly, for our place in the cosmos. But what's fascinating and maybe surprising is how early some genuinely scientific observation began.
Oh, really? How early?
Well, even as far back as 340 BC, the Greek philosopher Aristotle provided remarkably robust arguments for a spherical Earth. This was in his book On the Heavens.
340 BC.
Wow. So he wasn't just guessing.
No, not at all. He wasn't just speculating, he was observing. He noticed the round shadow of Earth on the moon during lunar eclipses. That shadow shape could only happen if Earth itself was spherical.
That makes sense.
He also noted how the North Star's apparent position changed as you traveled north or south. It appears lower in the sky when viewed from more southerly regions.
Ah, okay. I see.
And even the simple sight of a ship's sails appearing over the horizon before its hull, that points directly to a curved surface. These are tangible proofs, really, in an age dominated by philosophy. He even tried to estimate Earth's circumference, though his value is about double the modern one. Still pretty impressive for the time.
Very impressive. But despite these sharp observations, Aristotle still clung to the idea that the Earth was stationary, right? At the very center of everything. Yes, absolutely. He believed everything orbited Earth in perfect circles. And the reason, mystical reasons, as Hawking puts it, he felt circles were ideal, perfect.
So it's quite a leap there from rigorous scientific observation to, philosophical preference.
It really is. It shows how even brilliant minds back then were influenced by their preconceived notions of perfection in cosmic order.
And this geocentric view, this Earth-centered view, it got cemented later, didn't it? by Ptolemy.
That's right, by Ptolemy in the 2nd century AD. He elaborated Aristotle's ideas into an incredibly complex, but quite ingenious for its time, model. Earth stood at the center, surrounded by 8 spheres carrying the moon, sun, and the known planets.
Fade spheres. Okay.
And to explain the planet's really complicated observed paths in the sky, their occasional retrograde motion where they appear to move backward for a bit,
That always seemed weird.
he introduced this intricate system of smaller circles called epicycles. Planets basically moved in circles on top of their larger circular orbits around Earth.
Circles upon circles sounds complicated.
It was. But it worked well enough for predictions at the time, and this model was widely accepted, even embraced by the Christian Church, as it conveniently placed humanity at the center of God's creation. And it left space beyond the outermost sphere for heaven and hell.
Ah, convenient.
Very, but it had observable flaws, like it predicted the moon should sometimes appear twice as large as other times, which, well, clearly isn't the case. Still, it persisted for over a millennium, incredible staying power.
So enter Nicholas Copernicus in 1514, a Polish priest, interestingly enough.
Yes, a cleric.
And he dared to suggest a simpler sun-centered model, heliocentric.
Mm-hmm. But cautiously. He circulated it anonymously at first.
Really? Why anonymously?
Well, probably for fear of being branded a heretic. You have to remember the context.
Right. Can you imagine the career risks for science back then? Challenging not just scientific orthodoxy, but powerful religious dogma.
It highlights the immense courage it took, really, to propose such radically new ideas.
And it took a while for his idea to catch on.
It truly did. Nearly a century for this heliocentric idea to be taken seriously by the broader community. The real death blow, the undeniable evidence against the Aristotelian Ptolemaic theory came in 1609.
Okay, what happened then?
That's when Galileo Galilei, using the newly invented telescope, observed Jupiter's moons.
Ah, the telescope changes everything.
It really does. This was a direct, undeniable observation showing that not everything had to orbit directly around the Earth. He saw these small satellites clearly revolving around Jupiter. That proved there could be other centers of orbit in the universe.
Couldn't they just make the old model even more complicated to account for that?
Well, theoretically, you could probably concoct incredibly complicated paths for these moons in the geocentric model, adding more epicycles. But Copernicus's sun-centered theory was just far, far simpler and more elegant.
Occam's razor, sort of.
Exactly. This dramatically highlights the importance of observation over pure philosophical thought. It was a key shift in scientific methodology, really the birth of modern science.
And Galileo's story, his clash with the church, it remains such a powerful reminder of science's need for independence, doesn't it?
Absolutely. His conflict with the Catholic Church, his steadfast belief that observation was key to understanding the world, even the fact that his second major book, Two New Sciences, had to be smuggled out of Italy for publication after his house arrest, all of it underscores his pivotal role.
It's ironic, isn't it? How often scientific truth clashes with established beliefs, and how often those who cling to the old ideas eventually, well, lose the argument.
History tends to favor observation. Just before Galileo, actually, Johannes Kepler had refined Copernicus's theory. He noticed planets moved in ellipses, not perfect circles.
Ellipses. Less perfect.
Exactly, a concept he initially found repugnant because of its perceived imperfection. He, like Aristotle, preferred the sort of divine perfection of circles. But the observational data compelled him. The math didn't lie.
So the data forced his hand.
Pretty much. But the full unifying explanation for why they moved in ellipses, why everything moved the way it did, came later, 1687, Sir Isaac Newton's Principia Mathematica.
Ah, Newton. Big one.
Arguably the most important single work ever published in the physical sciences. Just revolutionary.
Here's where it really gets profound, I think.
Mm.
Newton didn't just propose laws of motion, like how things move.
No, much more.
He developed the mathematics needed to analyze them calculus.
Yeah.
And he postulated universal gravitation.
Universal gravitation, the key idea. Everybody in the universe attracts every other body, a force proportional to their mass and inversely proportional to the square of the distance between them.
So bigger things pull harder, things farther away pull weaker.
Precisely. And it's this same force that causes objects to fall to the ground. Apples, planets, moons, all governed by the same law.
Though, as Hawking noted, the story about the apple actually hitting Newton on the head is probably not true, right?
Almost certainly apocryphal, yes. Newton himself merely stated that the idea of gravity came to him as he sat in a contemplative mood and was occasioned by the fall of an apple. But the universal principle it illustrates is truly profound.
And Newton's laws explain something Galileo had shown, that objects of different weights fall at the same rate. How did that work?
Right, so a heavier object has more gravitational pull acting on it, a greater force.
Yeah.
But it also has proportionally more mass, more inertia, more resistance to being accelerated.
Ah, okay.
And these two effects, the increased force and the increased resistance to acceleration, cancel each other out exactly. That's according to Newton's second law. Force equals mass times acceleration.
So the nth cancels out, basically.
Exactly, resulting in the same acceleration for all objects regardless of their mass, neglecting air resistance, of course.
And wasn't this shown dramatically on the moon?
Yes. Astronaut David R. Scott, during the Apollo 15 mission, he dropped a hammer and a feather simultaneously in the vacuum of the moon, and they hit the lunar surface at the exact same instant. A beautiful demonstration.
Wow. So with Newton, we finally had this universe governed by precise, calculable laws. The orbits of planets, the falling apple, the tides, all explained by this single elegant principle. It was a complete framework, it seemed.
It seemed complete. But interestingly, Newton himself still believed in absolute space, a fixed, unmoving backdrop against which all motion occurred.
Even though his own laws suggested motion is relative.
Exactly. His laws actually imply that there's no absolute standard of rest. He was even criticized for this by contemporaries like Bishop Berkeley, who called it an irrational belief because you couldn't actually measure this absolute space.
It shows that even the greatest minds can cling to prior assumptions, doesn't it? Even ones that seem to contradict their own discoveries.
It certainly does. And this leads us perfectly to the next huge shift in thinking. While Newton, and Aristotle before him, believed in absolute time, a universal clock ticking the same for everyone, everywhere, uniformly across the cosmos.
Yeah, that seems like common sense.
It does seem like common sense, and that idea works perfectly fine for apples and planets moving at everyday speeds. But as we'll see, it breaks down entirely for things moving at extreme speeds, close to the speed of light.
Ah, and that's where Einstein comes in.
That is precisely where Einstein fundamentally rewired our understanding of reality, shattering our intuitions about space and time.
Okay, so the journey to relativity really kicks off with light. Something we see every day, but it turns out to be, well, really weird.
Very weird and very fundamental. Back in 1676, the Danish astronomer Ole Christensen Romer first showed that light travels at a finite speed, not instantaneously.
How did he figure that out? That sounds difficult.
It was ingenious.
Yeah.
He was observing the moons of Jupiter, specifically when they passed into Jupiter's shadow, their eclipses. He noticed variations in the timing of these eclipses. As Earth moved farther away from Jupiter in its orbit, the eclipses seemed to occur later than predicted.
Ah, so the light took longer to reach Earth.
Exactly. He deduced this delay was due to the extra time light needed to travel the increased distance between Jupiter and Earth. His actual estimate for light speed was a bit off, but the breakthrough was monumental, proving light had a finite cosmic speed limit. It wasn't instantaneous.
That's huge conceptual leap.
Enormous. Then, fast forward to 1865, James Clerk Maxwell achieved this truly remarkable unification in physics. He combined the existing partial theories describing electricity and magnetism into a single comprehensive theory. Electromagnetism. And Maxwell's equations, these beautiful mathematical statements, predicted the existence of wave-like disturbances in this combined electromagnetic field. And crucially, that these waves would travel at a fixed, constant speed.
And that speed was?
The speed of light. This led to the stunning realization that light itself is an electromagnetic wave, just ripples in the electromagnetic field.
Wow. Okay.
But this, in turn, raised a critical question. What was light traveling through? If it's a wave, it needs a medium, right? Like sound needs air, or water waves need water.
Right.
So the prevailing idea was this mysterious medium called the ether, or ether. An invisible, undetectable substance filling all of space, providing the medium for light waves.
The ether. Sounds a bit mystical now.
It does. And here's where the surprising facts hit hard. The Michelson-Morley experiment in 1887 set out specifically to measure Earth's speed through this hypothetical ether.
How would they do that?
Their reasoning was simple. If Earth is moving through a stationary ether, then the speed of light should appear different depending on whether you measure it in the direction of Earth's motion or perpendicular to it, like swimming with or across a current.
Makes sense. You'd expect a difference.
You would. But to their great surprise, as Hawking puts it, the speed was exactly the same in all directions. No difference whatsoever.
No ether.
No detectable ether effect. No difference in light speed. It was a profoundly baffling result that completely shook the foundations of classical physics.
What did people do? Just accept it.
Not immediately. This null result was a profound shock. For nearly 2 decades, physicists really struggled to explain it away. They came up with complex, sort of ad hoc ideas, like maybe objects physically contract in the direction of their motion through the ether, or maybe clocks slow down, trying to patch up the old theory.
Right, trying to save the ether concept.
Exactly. But then, in 1905, along comes this hitherto unknown clerk in the Swiss Patent Office, Albert Einstein.
Einstein, working in a patent office. Amazing.
And he proposed this radical, yet elegantly simple solution. The ether was completely unnecessary. All those complex explanations just vanished if you were simply willing to abandon one deeply ingrained idea.
Which was?
The idea of absolute time.
Back to absolute time again.
Back to absolute time. Einstein said, let's just get rid of it. And this single, simple conceptual leap had monumental consequences, fundamentally reshaping our entire understanding of the universe.
So what exactly did Einstein's special theory of relativity state? What was the core idea?
Its fundamental postulate, the bedrock assumption, was that the laws of science should be the same for all freely moving observers, no matter what their speed is.
Okay, that sounds reasonable.
And crucially, linked to that, all observers, regardless of their relative motion, should measure the same constant speed of light. Always c.
Wait, the speed of light is the same for everyone, no matter how fast they're moving.
Exactly. That's the really counterintuitive part. If someone is flying towards you in a spaceship at half the speed of light and they turn on their headlights, you don't measure the light coming towards you at 1.5 times c. You still measure it at c.
That doesn't make sense in everyday terms.
It doesn't. It violates our everyday intuition built on slow speeds. But this is where it truly gets mind-bending, because this simple premise leads to astonishing conclusions about the fabric of reality itself.
Like what? What are the consequences?
Well, first, and perhaps the most famous equation in all of science, EMC-FCO4. The equivalence of mass and energy.
Energy is mass, and mass is energy.
Precisely. This equation means that energy itself possesses mass, and vice versa. A consequence of this is that as an object with mass approaches the speed of light, the energy associated with its motion adds significantly to its effective mass.
So it gets heavier the faster it goes.
Effectively, yes.
Yep.
Its resistance to further acceleration increases. This means its mass increases infinitely as it nears c, requiring an infinite amount of energy to push it any faster.
So nothing with mass can ever reach the speed of light.
Correct. Nothing with intrinsic mass can ever reach or exceed the speed of light. Only massless particles, like photons, the particles of light, can travel at c because they have no rest mass to begin with. This sets a fundamental universal speed limit.
Wow. Okay. MNCM.
Well, the second big consequence, it completely revolutionized our ideas of space and time. As we touched on, no more absolute time, ticking universally for everyone.
Right, because the speed of light has to be constant for everyone.
Exactly. If all observers must agree on the speed of light, but they can disagree on the distance light travels, because space itself isn't absolute, their measurements of distance can differ depending on their relative motion.
Then they must also disagree on the time taken.
Precisely. Because speed equals distance divided by time. If speed is constant for all, but distance is relative, then time must also be relative to make the equation work.
So each observer has their own personal clock, their own measure of time.
Exactly. Each observer has their own measure of time as recorded by their own clock. Time becomes personal, subjective, interwoven with an observer's motion. Time is not absolute.
That's hard to grasp. My time isn't necessarily your time.
It isn't if we're moving relative to each other. Observers moving relative to each other will assign different times and different positions to the same event. Yet, crucially, all these different measurements are equally valid, and they are mathematically related by Einstein's equations, the Lorentz transformations.
And we even use this today.
We do. Think about the definition of the meter, our fundamental unit of length. It's now defined based on the distance light travels in a tiny fraction of a second. So distance is intrinsically linked to time via the constant speed of light.
So space and time aren't separate things anymore.
They aren't. This leads directly to the concept of space-time. Time is not a separate, independent entity ticking away. It's combined with the three dimensions of space into a single, unified, four-dimensional entity, space-time.
My brain is already twisting trying to visualize 3 dimensions sometimes, let alone 4. How
Yeah.
can we even begin to wrap our heads around that?
It's a challenge for everyone, honestly. Hawking suggests thinking of it with diagrams. Imagine time flowing upwards on the page and maybe one spatial dimension horizontally.
Okay, like a graph.
Sort of. Now imagine a flash of light happens at a particular event, a point on this diagram. As time goes on, moving up the page, this light spreads out as an expanding circle, or sphere if we included more space dimensions.
Mhm.
If you stack snapshots of these expanding circles one above the other in the space-time diagram, you create a cone shape, the future light cone of that event.
Ah, okay, the cone represents where the light can reach.
Exactly. Similarly, there's a past light cone representing all the events that could have sent light to the event. These light cones mark out the possible paths of light, and because nothing can travel faster than light, they define the future and past relative to that specific event.
What about things outside the cones?
Events outside these cones are in what's called the elsewhere. They can neither influence the event if they're outside the past cone, nor be influenced by the event if they're outside the future cone, because information limited by light speed can't travel between them.
So this light cone concept helps us understand causality, basically.
Precisely. It helps us understand why, for example, if the sun were to suddenly, hypothetically, vanish at this very moment, we wouldn't know about it for 8 minutes.
Because the light, or the lack of light, hasn't reached us yet.
Exactly. The event of the sun vanishing would be in our elsewhere for those 8 minutes. Its future light cone, or rather the edge of the shadow cone, would not yet have reached Earth. That's a powerful illustration of this structure.
And it explains why looking at distant stars is like looking back in time.
Exactly. When we see a galaxy millions of light years away, we're not seeing it as it is now. We're seeing it as it was millions of years ago because the light has taken that immense amount of time to travel across space to reach our telescopes. The light from the most distant objects we've ever detected left billions of years ago, giving us a literal glimpse into the universe's deep past.
Okay, so special relativity deals with constant speeds and gives us space-time and inertia.
But it didn't include gravity, right?
Correct. Special relativity was incredibly powerful, but it was incomplete because it didn't account for gravity. And Newton's theory of gravity, with its idea of instantaneous action at a distance,
Clashed with the speed limit of light. Exactly. It said objects attracted each other instantaneously across space, which directly conflicted with the cosmic speed limit established by special relativity. So Einstein knew something had to give. After years of intense intellectual struggle, in 1915, he gave us his general theory of relativity, a truly monumental leap in understanding gravity.
and the core idea here was completely different from Newton's force.
Completely different. The revolutionary idea in general relativity is that gravity isn't a force in the traditional sense, like magnetism or electricity, pulling objects toward each other across empty space.
So what is it then?
Instead, gravity is a consequence of space-time itself not being flat, but being curved or warped by the distribution of mass and energy within it.
Mass and energy warp spacetime.
Yes. Think of it like placing a heavy bowling ball on a stretched rubber sheet. The sheet curves around the ball.
Okay.
Now, if you roll a smaller marble nearby, it doesn't roll straight across the sheet. It follows the curve created by the bowling ball.
So it looks like it's being attracted to the bowling ball.
Exactly. Objects, like planets orbiting the sun, don't so much fall toward the sun due to a pulling force. Rather, they are following the straightest possible path, what's called a geodesic, in this curved four-dimensional spacetime. The curvature tells matter how to move.
So the Earth isn't being pulled by the sun's gravity in the Newtonian sense, but is essentially following a straight line in a spacetime that's been curved by the sun's immense mass. That's a huge conceptual shift.
It's enormous. And this wasn't just a philosophical change. This theory made startling predictions that could actually be tested, predictions that diverged, even if subtly sometimes, from Newton's theory.
Like what kind of predictions?
Well, for most planets, the predictions for their orbits were almost identical to Newton's, which is good because Newton's theory worked very well for most things. But for Mercury, the planet closest to the sun, where the sun's gravitational field is strongest and space-time is most curved.
Ah, the extreme case.
Right. General relativity predicted a tiny difference. It predicted a slight precession, a slow rotation, of the long axis of Mercury's elliptical orbit, about 1 degree every 10,000 years.
Tiny. Could they even measure that?
Yes, astronomers had actually already observed this tiny anomaly in Mercury's orbit before 1915, and Newton's theory couldn't fully explain it. Einstein's theory predicted it perfectly. It served as one of the first crucial, successful confirmations of general relativity.
Wow. Okay, what else? What about light?
The bending of light. This is another famous prediction. General relativity predicted that light rays, like everything else, would follow these geodesics, these straightest paths in curved spacetime. That means gravity bends light.
Gravity bends light. How could they test that?
The idea was to look at stars whose light passed very close to the sun on its way to Earth. Normally, you can't see stars near the sun because the sun is too bright. But during a total solar eclipse, when the moon blocks the sun's disk, you can briefly see those stars. The prediction was that the apparent position of these stars would be shifted slightly outwards, because the sun's gravity would bend their light rays as they pass by.
And did they see it?
They did. This was famously tested in 1919 during a total solar eclipse by a British expedition led by Sir Arthur Eddington. They measured the positions of stars near the eclipsed sun and found they were deflected, just as Einstein predicted.
Amazing confirmation.
It was hailed as a triumph. Though, as Hawking honestly notes, the measurements were actually very difficult, and the early results had quite large errors. He cheekily suggests it might have been sheer luck, or perhaps the observers knowing the result they wanted to get, that led to the immediate confirmation.
Bit of scientific realism there.
Indeed. But later, much more accurate observations using radio waves from distant quasars have proved the bending of light by the sun's gravity very precisely. Einstein was right.
Okay, any other key predictions?
Yes, another crucial one, with profound implications for our concept of time again. Time appears to run slower near massive bodies.
Slower. How does that work?
Think about light escaping from a massive object like a star or a planet. It has to climb out of the gravitational well. As it does, it loses energy. Since the energy of light is related to its frequency, how fast the wave crests arrive, lower energy means lower frequency.
Okay.
Lower frequency means the time interval between successive wave crests is longer. So, to an observer far away, time itself on the surface of the massive body appears to be running slower. Clocks tick slower in stronger gravity.
Has that been tested?
Yes, very accurately. It was confirmed back in 1962 using extremely precise clocks placed at the top and bottom of a water tower. The clock nearer the Earth, experiencing a slightly stronger gravitational field, was measured to run detectably slower than the clock at the top.
Incredible. And does this have any practical effect?
Absolutely. This isn't just some academic curiosity. It's crucial for modern navigation systems like GPS. GPS relies on receiving extremely precise time signals from satellites orbiting Earth. These satellites are higher up in a weaker gravitational field than we are on the surface. So their clocks run slightly faster than clocks on the ground according to general relativity.
Okay.
Also, the satellites are moving very fast, which means their clocks run slightly slower due to special relativity's time dilation effect. You have to account for both effects: clocks running faster due to weaker gravity and slower due to their speed. If you ignore these relativistic corrections predicted by both special and general relativity,
What happens?
your calculated GPS position would drift off by several miles every single day. The system simply wouldn't work accurately without Einstein's theories.
Wow. So relativity isn't just abstract theory. It's built into technology we use every day.
Absolutely essential technology. And this brings us back to this idea of personal time and the famous twins paradox.
Right. The twin who travels into space near light speed comes back younger.
Exactly. One twin stays on Earth, the other goes on a long journey in a very fast spaceship, traveling near the speed of light, then turns around and comes back. When they reunite, the traveling twin is found to be much younger than the Earthbound twin.
Is it really a paradox?
In relativity, it's not actually a paradox at all. It's a direct consequence of each individual having their own measure of time, their own proper time, which depends on their motion, special relativity, and their location within gravitational fields, general relativity. The traveling twin, experiencing significant time dilation due to their high speed and potentially different gravitational environments, would indeed age more slowly relative to the stationary twin. There is no absolute universal clock. Time truly is relative.
Okay, so we've established that time is relative, personal even. Now let's zoom way out from personal time to the timescale and structure of the entire universe.
Right. The big picture.
Our modern picture really began to take shape, you mentioned, around 1924. That's when Edwin Hubble made another monumental discovery.
Yes, Hubble again, a pivotal figure.
He proved that our Milky Way galaxy wasn't the entire universe, as many had thought. It was just one of many, many galaxies. Cosmic islands, really, separated by truly vast stretches of apparently empty space.
And he did this by painstakingly measuring the distances to these faint, fuzzy patches of light, then called nebulae. He used standard candles, certain types of stars, like Cepheid variables, whose intrinsic brightness, their luminosity, is known.
How does that help measure distance?
Well, if you know how bright a star truly is, its intrinsic luminosity, and you measure how bright it appears to us, you can calculate how far away it must be. Because light dims with distance following an inverse square law.
Ah, like a dimmer headlight seems farther away.
Exactly. By finding these Cepheid variable stars in distant nebulae like Andromeda and comparing their apparent brightness to their known intrinsic brightness, Hubble showed they were incredibly far away, far outside the bounds of our own Milky Way. They had to be entire galaxies in their own right.
So the universe suddenly got much, much bigger.
Immensely bigger, almost overnight, cosmologically speaking. But the key discovery, the really revolutionary one, came from observing the light emitted by these distant galaxies.
Okay, what about the light?
He looked at their spectra, the rainbow of colors produced when you split their light, and he used the Doppler effect. Just like a siren's pitch changes as an ambulance moves towards or away from you.
Higher pitch coming towards a lower pitch going away.
Right. The same principle applies to light waves. Objects moving towards us have their light waves compressed, shifted towards the blue end of the spectrum, blue shifted. Objects moving away from us have their light waves stretched out, shifted toward the red end of the spectrum, they are redshifted.
Okay, redshift means moving away.
Correct. And Hubble found that almost all the distant galaxies he observed were redshifted, meaning they were overwhelmingly moving away from us. But even more surprising was the correlation he found.
Which was?
The farther away a galaxy was, based on his distance measurements, the greater its redshift, and therefore the faster it was receding from us.
Whoa. So farther means faster.
Farther means faster. This was the groundbreaking discovery that utterly transformed cosmology. The universe is not static, it is expanding.
It's not just galaxies flying away through space, is it?
No, that's a key point. It's more accurate to think of space itself stretching, like the surface of an expanding balloon. The galaxies are like dots drawn on the balloon. As it inflates, all the dots move farther apart from each other, and dots farther away move apart faster.
So there's no single center to the expansion. It looks the same from any galaxy.
Exactly. From any galaxy, it would look like all the others are moving away, with the farthest ones moving fastest. This expansion was a huge intellectual revolution. It fundamentally overturned centuries, millennia even, of belief in a static, unchanging universe.
Looking back, you said even Newton's theory hinted at this.
Yes, with hindsight, it's easy to wonder why no one had thought of it before. Newton's own theory of gravity, with its universal attraction, actually implied that a static universe filled with matter would be inherently unstable. It should inevitably collapse under its own gravity.
So why didn't people predict expansion?
The belief in a static universe was just so incredibly strong. Even Einstein, when he first formulated general relativity in 1915, found his equations predicted an expanding or contracting universe. But he couldn't accept it.
He didn't believe his own math.
Not initially. The idea of a dynamic universe seemed wrong. So he introduced an extra term into his equations, a sort of mathematical fudge factor he called the cosmological constant. This acted like a repulsive force to perfectly balance gravity and force a static solution.
He later regretted that.
Famously called it his biggest blunder after Hubble's observations provided clear observational proof that the universe was expanding. The data forced his hand, just like it forced Kepler's.
But it wasn't Einstein who first embraced the idea of an expanding universe within the framework of general relativity, was it?
No, incredibly, it wasn't. It was a Russian physicist and mathematician named Alexander Friedmann back in 1922, several years before Hubble's observations.
Wow. How did he figure it out?
Friedmann started with two very simple but powerful assumptions about the universe on large scales. First, that it looks the same in every direction, isotropic. Second, that it looks the same from every location, homogeneous.
The universe is basically uniform on the grandest scale.
Yes, the cosmological principle. Based just on these two assumptions and Einstein's original equations, without the cosmological constant, Friedmann mathematically proved that the universe couldn't be static. His model showed it must either be expanding or contracting. He predicted exactly what Hubble found observationally years later. a stunning example of the predictive power of theoretical physics.
Amazing. And was Friedman's first assumption that the universe looks the same in all directions ever confirmed?
Oh yes, dramatically confirmed in 1965 by Arno Penzias and Robert Wilson, two American physicists working at Bell Labs in New Jersey.
Labs. What were they doing?
They were testing a very sensitive microwave antenna originally designed for satellite communication, and they kept picking up this persistent, faint background noise like a hiss in their receiver.
Boys.
That was the mystery. It wasn't coming from Earth, it wasn't the sun, it wasn't even from our galaxy. It seemed to be coming equally from all directions in the sky, day and night, all year round. It was incredibly uniform.
So what do they think it was? Interference.
They tried everything to rule out interference. They checked their equipment, rebuilt parts of it. They even famously...
The bird dropping story.
The bird droppings story. They apparently found pigeons nesting in the antenna horn and suspected their residue might be causing the noise, so they cleaned it all out meticulously.
Wow.
The noise was still there, unchanged. They eventually realized, after talking to physicists at nearby Princeton University, that they had stumbled upon something extraordinary.
What were the Princeton guys doing?
Meanwhile, at Princeton, a team led by Bob Dick and including Jim Peebles were independently working on calculations based on George Gamow's earlier ideas. They were predicting that if the universe began in a very hot, dense state, the Big Bang, there should be a faint afterglow radiation left over from that early era, cooled by the expansion to just a few degrees above absolute zero, and appearing as microwaves today. They were actually building an experiment to look for it.
So Penzias and Wilson found what Dick and Peebles were looking for.
Exactly. Penzias and Wilson had, by complete serendipity, found the cosmic microwave background radiation, or CMB. This faint microwave glow permeating all of space is the residual heat from the Big Bang, a remarkably accurate confirmation of Friedman's assumption of isotropy and a cornerstone of modern cosmology. They even apparently joked about calling the first signals LGM 1-4 for little green men before realizing its true cosmic origin.
Huh. That's incredible. So the CMB tells us the universe started hot and dense.
Yes. The cosmic microwave background radiation, which has now been measured with incredible precision by satellites like COBE, WMAP, and Planck, tells us the universe began in an incredibly hot, dense state. The tiny variations, the slight temperature fluctuations in the CMB across the sky are also crucial. They are the seeds, the primordial density fluctuations from which all the large-scale structures we see today, galaxies, clusters of galaxies eventually form through gravitational collapse.
So this is the foundation of the hot Big Bang model.
Precisely. The standard model of cosmology. It posits the universe began from a state of near-infinite density and temperature. Hawking says zero size and infinite hotness is the classical extrapolation, and then rapidly expanded and cooled over billions of years to become the universe we observe today.
So if the universe is expanding, what's its ultimate fate? You mentioned Friedman's models offered different possibilities.
That's right. Friedman's solutions to Einstein's equations, based on those assumptions of homogeneity and isotropy, give three main possibilities for the universe's future, depending on its average density.
Okay, what are they?
Possibility 1. If the average density of matter and energy in the universe is high enough, gravity will eventually overcome the expansion. The expansion will slow down, stop, and then reverse. The universe will start contracting, eventually collapsing back into a state of infinite density, a big crunch.
The opposite of the Big Bang.
Exactly.
Yeah.
Possibility 2. If the density is too low, gravity won't be strong enough to halt the expansion. The universe will continue expanding forever, getting colder, darker, and emptier as stars burn out and matter disperses. This is often called the Big Freeze, or heat death.
Sounds bleak.
It does. Possibility 3. The borderline case. If the density is exactly at a specific critical value, the universe will expand forever, but the expansion rate will continuously slow down, asymptotically approaching zero, but never quite stopping or reversing. It just coasts.
So which one is it? Do we know?
To answer that definitively, we need to precisely measure two key things: the universe's current expansion rate, the Hubble constant, and its average density. Measuring these accurately is incredibly difficult. For a long time, observations suggested we were very close to the critical density, maybe slightly below.
And what about the shape of space in these models?
Yes. In the first model, the closed universe that recollapses, space itself would be finite, but have no boundary. It would have positive curvature, like the surface of a sphere in 3 dimensions.
Finite but unbounded. Like you could travel in a straight line and end up back where you started.
Theoretically, yes. You could go right around the universe and end up where you started, although you'd probably run out of time before the Big Crunch, and relativity forbids faster than light travel anyway. In the open universe, expanding forever, density below critical, space would have negative curvature, like a saddle shape, and be infinite. In the flat or critical universe, space would be Euclidean, flat, and also infinite.
Okay, that's a lot to visualize. But the key point is all these models point backwards to a beginning, right?
Here's the kicker.
Yes.
All of the Friedman solutions, when extrapolated backwards in time, point to a moment when the distance between any 2 points in the universe was zero, a Big Bang singularity in the past, a point where the universe had zero size, infinite density, and infinite space-time curvature.
And that's where our current physics breaks down.
That's where general relativity, and indeed all known physical laws as we understand them, would cease to be valid. They predict their own failure at the singularity. It means we can't use these laws to predict what happened before the Big Bang, or even at the Big Bang. It effectively marks the beginning of time as far as our scientific models are concerned.
That idea of a beginning in time, it wasn't popular with everyone, was it?
No, definitely not. Many people, for various reasons, philosophical, scientific, even religious, disliked the idea that time itself had a definite beginning. This discomfort led to alternative theories, most notably the steady-state theory proposed in the 1940s by Bondi, Gold, and Hoyle.
What was their idea?
They proposed that the universe, although expanding, looked roughly the same at all times on a large scale. To maintain a constant density as space expanded, they suggested that new matter was continuously being created out of nothing, filling in the gaps.
Continuous creation, that sounds convenient.
It avoided the thorny issue of a beginning, yes, but observations eventually ruled it out quite decisively. Counts of distant radio sources showed the universe looked different in the past, more sources back then, and crucially, the discovery of the cosmic microwave background radiation, that afterglow of a hot, dense past, directly contradicted the steady-state idea that the universe was unchanging in time.
So the Big Bang model won out.
The evidence strongly favored it. And then these singularity theorems, developed in the 1960s and rigorously proven by Roger Penrose and Stephen Hawking himself, provided a powerful theoretical argument. They showed that, under very general conditions, general relativity demands a singularity in the past, a beginning like the Big Bang, and potentially singularities in the future, inside black holes.
But you said this also means general relativity is incomplete.
Precisely. By predicting points like the Big Bang singularity, where its own equations yield infinities and break down, general relativity signals its own incompleteness. It tells us that to understand the very beginning of the universe, or the hearts of black holes, we need a new theory. We need a theory that combines general relativity with the other great pillar of 20th century physics.
Quantum mechanics.
Quantum mechanics. We need a theory of quantum gravity. This realization forced physicists to turn from the unimaginably vast scales of cosmology to the unimaginably tiny scales of the quantum realm, seeking answers to the universe's biggest questions in its smallest constituents.
Okay, so just as our understanding of the cosmos evolved dramatically, so did our picture of matter itself, or what things are actually made of.
Absolutely. A parallel revolution, really. We went from Aristotle's 4 classical elements, earth, air, fire, water, which dominated thinking for centuries.
Seems quaint now.
It does. To the idea proposed by the ancient Greek philosopher Democritus of indivisible fundamental units called atoms. But for centuries, this was purely a philosophical debate. Are things infinitely divisible, or is there a smallest piece?
When did atoms become actual science?
The first real empirical support came in 1803 with John Dalton. He showed how the idea of atoms combining in specific ways could perfectly explain why chemical compounds always formed in fixed whole number ratios. This gave the atomists their first solid scientific footing.
And then Einstein weighed in.
Yes, the atomists finally won the argument decisively in the early 20th century. One key piece was Einstein's 1905 paper explaining Brownian motion, the random jiggling movement of tiny dust particles suspended in a liquid. He provided crucial, quantifiable evidence that this movement was caused by the particles being constantly bombarded by unseen, moving atoms of the liquid.
So atoms were real, but they weren't the end of the story. They weren't indivisible.
Not at all. Just as atoms became accepted, experiments started showing they had internal structure. J.J. Thomson discovered the electron in 1897, a tiny, negatively charged particle. Then Ernest Rutherford, through his famous gold foil experiment, showed in 1911 that atoms consist mostly of empty space, with a tiny, dense, positively charged nucleus at the center and the electrons orbiting it somehow.
Like a miniature solar system.
That was the early picture, though it had problems. And then we kept going deeper. The nucleus itself was found to contain positively charged protons and neutral neutrons. And for a while, protons, neutrons, and electrons were thought to be the fundamental elementary particles.
But they weren't.
Nope. Experiments in the 1960s smashing particles together at higher and higher energies revealed that even protons and neutrons weren't elementary. They were made of even smaller particles called quarks.
Quarks, okay. Just one kind.
Not just one kind. It got more complicated. We now know there are 6 different flavors of quarks with whimsical names. Up, down, strange, charmed, bottom, and top.
Up, down, strange, charmed, bottom, top. Quite a collection.
Indeed. Protons are made of 2 up quarks and 1 down quark. Neutrons are 1 up and 2 downs. And each quark flavor also comes in 3 different colors, red, green, or blue.
Colors. Are they actually colored?
No. As Hawking points out, these are just labels, like positive and negative charge are labels. Quarks are far too small to actually have color in the visible light sense. These color labels are part of the theory called quantum chromodynamics, or QCD, which describes how quarks interact via the strong nuclear force.
So what we consider elementary keeps changing.
Exactly. It depends directly on the energy scales we can probe. Higher energy particle accelerators act like more powerful microscopes, allowing us to resolve smaller and smaller structures. We keep finding smaller particles, or rather, evidence for them. But theoretically, with the current standard model of particle physics, which includes quarks, electrons, neutrinos, and the force carriers, we might be close to the ultimate building blocks of nature as we currently understand them.
And quantum mechanics is key to understanding all this.
Absolutely essential. And here's where the classical deterministic view of physics, championed by Newton and Laplace, truly breaks down. Heisenberg's uncertainty principle, formulated in 1927.
The uncertainty principle, what does it say again?
It states that you can never be exactly sure of both a particle's position and its velocity or momentum simultaneously. There's a fundamental limit to the precision. The more accurately you measure one quantity, the less accurately you can possibly know the other.
So you can know where it is or where it's going, but not both perfectly.
Precisely. Which means Laplace's 18th century dream of a completely deterministic universe where if you knew the exact position and velocity of every particle at one moment, you could, in principle, predict the entire future is definitively out the window. There's an inherent unavoidable fuzziness or unpredictability built into the very fabric of reality at the quantum level.
Wow, that's a fundamental shift.
It is. This principle, along with Max Planck's earlier quantum hypothesis that energy, like light, is emitted and absorbed in discrete packets or quanta, led to the development of the full theory of quantum mechanics in the 1920s by Schrödinger, Heisenberg, Dirac, and others.
And what does quantum mechanics tell us about particles?
In quantum mechanics, particles don't behave just like tiny billiard balls with definite positions and velocities. They also behave like waves, and waves behave like particles. This is wave-particle duality.
So they're both waves and particles. How does that work?
It means they don't have definite classical properties until you measure them. Instead, they exist in a quantum state, which is described by a wave function. This wave function represents a combination of possibilities, a superposition of different positions and velocities, each with a certain probability. It's not about what the world is in some absolute sense prior to observation, but about the probabilities of what we will observe when we make a measurement.
That sounds weird. Probabilities, not certainties.
It is weird. Einstein famously hated this aspect, saying God does not play dice. But experiment after experiment has confirmed the probabilistic nature of quantum mechanics. And this duality leads to observable effects like interference.
Interference, like with light waves.
Exactly. Like the shimmering colors you see in soap bubbles or oil slicks, caused by light waves reflecting off the top and bottom surfaces interfering with each other, or the famous double slit experiment.
Ah, the double slit experiment. What happens there?
If you fire individual particles, like electrons, one at a time towards a barrier with 2 narrow slits, you find something amazing. Even though each electron presumably goes through only one slit or the other, the pattern that builds up on a screen behind the slits shows an interference pattern alternating bright and dark bands exactly as if each electron were a wave passing through both slits simultaneously and interfering with itself.
Each electron interferes with itself.
It appears so, as long as you don't try to detect which slit it went through. This wave-particle duality is fundamental to understanding atoms.
How does it help with atoms? You mentioned classical atoms should collapse.
Right. Classically, an orbiting electron should continuously radiate energy and spiral into the nucleus in a fraction of a second.
Yeah.
But quantum mechanics, specifically another key principle discovered by Wolfgang Pauli in 1925, prevents this. It's called the Pauli exclusion principle.
Exclusion principle, what does that exclude?
It applies to a class of particles called fermions, which includes electrons, protons, neutrons, and quarks, basically, the particles that make up matter. They all have a quantum property called spin equal to half-half. Pauli's principle states that two identical spin half particles cannot occupy the exact same quantum state simultaneously. They can't have both the same position and the same velocity, or more accurately, the same set of quantum numbers, including spin orientation.
So they kind of push each other away.
In effect, yes. This quantum repulsion prevents electrons in an atom from all piling into the lowest energy state near the nucleus. They have to occupy distinct orbits or energy levels. This is what gives atoms their structure, their size, and their chemical properties. It prevents matter from collapsing into an infinitely dense soup. Without the exclusion principle, the universe would be a radically different and uninhabitable place.
So if matter is made of these tiny particles obeying quantum rules, what holds it all together? What are the forces?
The forces. Quantum mechanics describes the fundamental forces of nature in a new way, too. Instead of forces acting at a distance, it describes them as being mediated or carried by the exchange of other types of particles. These are the force-carrying particles.
Like passing a ball back and forth.
Exactly like that analogy. These force-carrying particles all have integer spin, 0, 1, or 2, unlike the matter particles. They are often called bosons. These exchanges involve virtual particles that pop into existence for a brief moment, carrying the force, and then disappear. They aren't directly detectable like real particles, but their exchange creates measurable effects, like the electromagnetic repulsion between two electrons or the gravitational attraction making the Earth orbit the Sun.
And these force carriers don't obey the exclusion principle.
Correct. Because they have integer spin, they are bosons, not fermions. This means many virtual particles can be exchanged, allowing for strong forces to build up.
Okay, so how many fundamental forces are there in this picture?
We currently recognize 4 fundamental forces of nature. First, the gravitational force. As we discussed, it's described by general relativity. In the quantum picture, it's thought to be carried by a hypothetical spin 2 particle called the graviton. Gravity is by far the weakest of the 4 forces, but it's universal. It affects everything with mass or energy, and it's long range. It's always attractive. Detecting individual gravitons, or even real gravitational waves, ripples in space-time caused by accelerating masses, is incredibly difficult because the force is so weak. Though gravitational waves have now been directly detected, confirming another prediction of general relativity.
Okay, gravity. What's next?
Second, the electromagnetic force. This is much, much stronger than gravity, about 1 followed by 42 zeros times stronger. It acts only on particles that carry an electric charge, like electrons and quarks. It can be attractive between opposite charges or repulsive between like charges. Because large objects like planets and stars usually have roughly equal amounts of positive and negative charge, the net electromagnetic force between them is very small, which is why gravity dominates on astronomical scales.
And what carries the electromagnetic force?
It's carried by a massless spin 1 particle called the photon. We observe real photons directly as light, radio waves, X-rays, all forms of electromagnetic radiation. Virtual photon exchange is responsible for binding negatively charged electrons to positively charged nuclei to form atoms, and for all chemical bonding between atoms. So electromagnetism underlies basically all of chemistry and biology.
Okay, gravity, electromagnetism. What else?
Third is the weak nuclear force. This force is responsible for certain types of radioactivity, like beta decay, where a neutron inside a nucleus can turn into a proton, emitting an electron and an antineutrino. It's called weak because it's weaker than electromagnetism and the strong force, and it also has a very short range. It acts on all the matter particles, quarks and leptons like electrons and neutrinos, but not on force-carrying particles like photons or gluons.
Was this one harder to understand?
It wasn't well understood until the 1960s. A major breakthrough came in 1967 when Abdus Salam and Steven Weinberg independently proposed a theory that unified the weak force with the electromagnetic force. This is known as the electroweak theory.
Unified them. Like
Yeah.
Maxwell unified electricity and magnetism.
Exactly. Their theory showed that at very high energies, such as those present in the very early universe, the electromagnetic force and the weak force are actually indistinguishable. They are different aspects of a single underlying electroweak force.
Why do they seem different now, then?
This is explained by a concept called spontaneous symmetry breaking. At high energies, the symmetry between the forces is apparent. But as the universe cooled below a certain critical temperature, the symmetry was spontaneously broken, causing the forces to manifest differently. It's like a roulette ball spinning at high speed. It's equally likely to fall into any numbered slot in symmetry. But once it slows down and falls into one specific slot, say number 7, the symmetry is broken.
And the weak force carriers.
The electroweak theory predicted the existence of force carriers for the weak interaction. 3 massive spin-1 particles called vector bosons, the W plus, the W and 0 particles. Their large mass explains the short range and weakness of the weak force at low energies. These particles were triumphantly discovered experimentally in 1983, confirming the electroweak theory.
Amazing. Okay, there's 3 forces. What's the 4th?
The 4th and final one is the strong nuclear force. As the name suggests, this is the strongest of the 4 fundamental forces, but it has the shortest range, acting only within the nucleus of an atom.
What does it do?
It performs 2 crucial roles. First, it binds quarks together inside protons and neutrons. Second, it holds the protons and neutrons themselves together within the atomic nucleus, overcoming the powerful electromagnetic repulsion between the positively charged protons, which would otherwise tear the nucleus apart.
And its force carrier.
The strong force is carried by spin-1 particles called gluons. There are 8 different types of gluons. Gluons have a unique property. They interact not only with quarks, but also with themselves. This self-interaction is key to the strong force's behavior.
And it has that weird confinement property.
Yes, a very curious property called color confinement. Quarks, as we said, carry a property called color charge, red, green, or blue. Gluons also carry color charge. The theory states that only combinations of quarks that are colorless, or white, can exist as free particles. For example, a proton consists of 1 red, 1 green, and 1 blue quark, making it colorless overall. A meson consists of a quark and an antiquark, whose color and anticolor cancel out. Individual quarks with a net color charge are never found in isolation. They are permanently confined inside composite particles like protons and neutrons. The force between quarks actually gets stronger as you try to pull them apart, like stretching a rubber band, making it impossible to isolate a single quark.
Wow. Gravity, electromagnetism, weak force, strong force, that's the set.
That's the set of fundamental forces described by the standard model of particle physics, which combines electroweak theory and QCD. It's incredibly successful at describing almost all experimental observations.
But people still talk about unifying them further, right? A grand unified theory.
Yes, the quest continues. The standard model treats the electroweak force and the strong force separately. The dream is to find a grand unified theory, or GUT, which would unite these 3 forces, electro, weak, and strong, into a single underlying framework. Just like electroweak theory unified electromagnetism and the weak force.
What did GUT predict?
GUTs predict that at extremely high energies, much higher than even the electroweak unification energies that likely only existed in the first tiny fraction of a second after the Big Bang, the strong force would have the same strength as the electroweak force, and they would all be different aspects of a single grand unified force.
Could we test that?
Not directly. The energies required are astronomical, far beyond anything achievable with current or foreseeable particle accelerators. You'd need an accelerator the size of the solar system, as Hawking puts it.
So it's purely theoretical.
Not entirely. GUTs can predict some potentially observable, albeit very rare, consequences at lower energies. The most famous prediction is that protons, the stable building blocks of atomic nuclei, might not be truly stable after all.
Protons could decay. Into what?
Yes, GUTs typically predict that protons can spontaneously decay into lighter particles, such as positrons, antielectrons, and pions. This is possible because at the grand unification energy scale, GUTs suggest there's no fundamental difference between a quark inside the proton and a lepton like a positron. The barrier between them breaks down.
Has this ever been seen?
Not yet. Experiments have been running for decades in deep underground laboratories, watching huge tanks of water for any sign of proton decay. So far, none have been definitively observed. This means the predicted proton lifetime must be incredibly long. Current limits are greater than 1 followed by 34 zeros years, which is vastly, vastly longer than the current age of the universe, about 14 billion years.
So maybe they are stable.
Or maybe their lifetime is just even longer than current GUT models predict. Or maybe the specific GUT model is wrong. But the possibility of proton decay is a tantalizing prediction. And interestingly, our very existence might hinge on processes related to GUTs.
How so? You mentioned this explains the matter-antimatter asymmetry.
Yes, that's a crucial piece of the puzzle that GUTs can potentially address. The universe today seems to be made almost entirely of matter, with very little antimatter. But if the Big Bang started with pure energy, it should have created equal amounts of matter and antimatter particles.
So where did all the antimatter go?
As the early universe expanded and cooled, matter and antimatter particles would have annihilated each other, producing radiation, photons. If they started in perfect balance, they should have wiped each other out completely, leaving only photons and maybe some neutrinos. Clearly that didn't happen. We're here.
So there must have been an imbalance.
Exactly. There must have been a slight excess of matter over antimatter created very early on, maybe only one extra matter particle for every billion matter-antimatter pairs. After all the annihilation finished, this tiny residue of matter was left over to form all the stars, galaxies, and us.
And GUTs can explain this imbalance.
Yes, GUTs provide a mechanism for this. It relies on subtle differences in the way matter and antimatter particles interact, specifically violations of certain fundamental symmetries.
Symmetries, like mirror images.
Exactly. For a long time, it was believed that the laws of physics obeyed three key discrete symmetries. C symmetry, charge conjugation. The laws are the same if you swap all particles with their antiparticles. P symmetry, parity. The laws are the same for a system and its mirror image, T symmetry, time reversal. The laws are the same if you run the process backward in time.
But these symmetries aren't perfect.
No. Experiments starting in 1956 by C.N. Yang, T.D. Lee, and C.S. Wu showed that the weak nuclear force violates P symmetry. The universe is not perfectly ambidextrous. It also violates C symmetry. For a while, it was thought the combined CP symmetry, swapping particles for antiparticles, A and D taking the mirror image, might still hold.
But that failed too.
Yes, experiments in 1964 by Cronin and Sitch showed that even CP symmetry is slightly violated by the weak force in certain particle decays. Now, there's a fundamental theorem in quantum field theory called the CPT theorem, which states that the laws of physics must be unchanged under the combined operation of C, P, and T together.
So if CP is violated,
Then, T symmetry, time reversal, must also be violated to compensate so that the overall CTT symmetry holds. This means the laws of physics are not exactly the same if you run time backward. There's a subtle arrow of time built into the fundamental interactions, specifically the weak force.
and how does this relate to the matter excess?
These CP, and therefore T violations, combined with interactions predicted by GUTs that don't conserve the number of quarks and leptons, allowing them to transform into each other, could have occurred in the rapidly expanding and cooling early universe when things were out of thermal equilibrium. These conditions, outlined by Andrei Sakharov, could have led to processes that produce slightly more quarks than antiquarks, or more leptons than antileptons. This tiny asymmetry, perhaps occurring just fractions of a second after the Big Bang, could be the reason why we live in a universe dominated by matter today. Our existence might be a relic of GUT physics and broken symmetries in the infant universe.
Okay, from the infinitesimally small building blocks and forces, let's swing back to the astronomically large and exotic. Let's talk about black holes.
Black holes. Yes, perhaps the most fascinating prediction of general relativity.
The idea isn't entirely new, though, is it? You mentioned Michel and Laplace.
That's right. The basic concept actually goes back to the late 18th century. John Michel, an English clergyman and natural philosopher, and later the French scientist Pierre-Simon Laplace, independently reasoned using Newton's theory of gravity and his corpuscular theory of light.
What was their argument?
They figured that if gravity affects light particles, then a star that was sufficiently massive and compact would have an escape velocity greater than the speed of light itself. Light emitted from its surface wouldn't be able to escape its gravitational pull. It would be a dark star.
A dark star. Basically a black hole in Newtonian terms.
Essentially, yes. But the idea was largely forgotten, partly because the wave theory of light became dominant in the 19th century, and it wasn't clear how gravity would affect waves. The modern concept really had to wait for Einstein's general relativity in the 20th century.
And understanding black holes means understanding how stars die.
Yeah.
Right?
Exactly. To understand how a black hole might form, you first need to understand the life cycle of a star. Stars form when huge clouds of gas, mostly hydrogen and helium, collapse inward under their own gravity.
Gravity pulls the gas together?
Yes. As the cloud contracts, the gas atoms collide more frequently, heating it up. Eventually, the core becomes so hot and dense that nuclear fusion ignites. Hydrogen nuclei start fusing together to form helium nuclei.
Like a giant hydrogen bomb.
In a controlled way, yes. This fusion process releases enormous amounts of energy, mostly as heat and light. This outward radiation pressure pushes against the inward pull of gravity, creating a balance. The star becomes stable and shines, like our own sun. Our sun has been doing this for about 5 billion years and will likely continue for another 5 billion or so.
But not all stars live that long.
No. The more massive a star is, the hotter its core needs to be to balance gravity, and the faster it burns through its nuclear fuel. Stars much more massive than the sun might only live for a few million years, a cosmic blink of an eye.
So what happens when they run out of fuel?
Once a star exhausts its primary nuclear fuel, first hydrogen, then helium, then heavier elements for massive stars, the outward pressure from fusion ceases. Gravity inevitably wins. The star begins to collapse inward. What happens next depends critically on the star's initial mass.
Okay, what are the possibilities?
In 1928, a young Indian physicist named Subramanian Chandrasekhar, while on a ship voyage to England, made a crucial calculation. He figured out the maximum mass the star could have and still support itself against gravitational collapse after it ran out of fuel, using the pressure generated by electrons due to the Pauli exclusion principle.
The exclusion principle again, holding stars up.
Yes. This outward electron degeneracy pressure can support stars up to about 1.4 times the mass of our sun. This limit is now called the Chandrasekhar limit. Stars below this limit end their lives by collapsing into incredibly dense objects called white dwarfs, about the size of the Earth, but with the mass of a star. They slowly cool and fade over billions of years.
Okay, so white dwarfs for stars up to 1.4 solar masses. What about stars more massive than that?
For stars more massive than the Chandrasekhar limit, electron degeneracy pressure isn't strong enough. Gravity crushes the star further. Electrons get squeezed into the atomic nuclei, combining with protons to form neutrons. The star collapses down to become a neutron star.
Made entirely of neutrons.
Pretty much. These are even denser than white dwarfs, packing the mass of 1 or 2 suns into a sphere only about 10 miles across. A teaspoonful of neutron star material would weigh billions of tons. Neutron stars are supported against further collapse by neutron degeneracy pressure, the exclusion principle acting between neutrons.
Neutron stars. Incredible objects. But is there a limit for them too?
Yes, there is thought to be a limit for neutron stars as well, though it's less precisely known, perhaps around 2 to 3 solar masses. But for stars significantly more massive than this, even neutron degeneracy pressure isn't enough to stop the relentless crush of gravity. They face, as Hawking put it, a big problem.
That's the big problem.
The problem is that, according to general relativity, nothing seems capable of halting the collapse. They should collapse completely, down to a point of infinite density.
A singularity.
A singularity. This implication was so shocking that many leading physicists, including Chandrasekhar's own mentor, Sir Arthur Eddington, and even Einstein himself, initially refused to believe it. They thought something must intervene to stop the collapse before infinite density was reached. Eddington was quite harsh towards Chandrasekhar's work initially.
Shows how hard it is to accept revolutionary ideas, even for brilliant scientists.
Absolutely. Chandrasekhar, despite eventually winning a Nobel Prize much later for this very work, was discouraged enough by the hostility that he temporarily abandoned the field.
So who figured out the full picture of this collapse?
The theoretical groundwork for understanding what happens during this final, catastrophic collapse was laid by Robert Oppenheimer, later famous for his role in the Manhattan Project, and his students in 1939, just before World War II interrupted much of this research.
What did Oppenheimer show?
Using general relativity, they described how, as a very massive star contracts beyond its stable limits, its gravitational field at the surface becomes incredibly strong. This intense gravity warps space-time so much that it starts to bend the paths of light rays significantly inward.
The light cones tilt inward.
Exactly. Light emitted from the surface finds it harder and harder to escape the star's gravitational grip. Eventually, when the star has shrunk down to a specific critical radius, called the Schwarzschild radius, which depends on its mass, the gravitational field becomes so overwhelmingly strong that the light cones at that radius are tilted inward so much that nothing, not even light itself, can escape.
The point of no return.
The point of no return. This boundary, this one-way membrane in space-time, is what we call the event horizon. Anything that crosses the event horizon from the outside can never get back out. It's trapped forever. The collapsed object inside is a black hole.
What would it look like if you were watching this happen from a safe distance?
It would be a very strange sight due to the effects of general relativity. As the star collapses towards its critical radius, time dilation becomes extreme. Clocks on the surface of the star would appear to tick slower and slower to you, the distant observer.
Time slows down near the forming black hole.
Yes. If an imaginary astronaut were falling onto the star and sending out light signals, say, every second according to their own clock, you would receive those signals at progressively longer intervals. The light itself would also be stretched to longer, redder wavelengths by the intense gravitational redshift.
So they'd appear to fade and slow down.
Exactly. As the star approaches the event horizon, the time interval between signals would become infinitely long, and the redshift would become infinite. The astronaut would appear frozen in time just outside the event horizon, fading from view as their light gets infinitely redshifted. You'd never actually see them cross the horizon. All that's left from your perspective is a region of space from which no light can escape a black hole.
But what about the astronaut falling in? What's their experience?
For the astronaut themselves, time would continue to pass normally according to their own clock. They wouldn't necessarily feel anything special as they cross the event horizon. It's not a physical barrier. However, well before they reach the center, assuming a stellar mass black hole, they would encounter immense tidal forces.
Tidal forces, like the moon causes tides on Earth.
Similar principle, but much, much stronger. The gravitational pull on their feet, assuming they fell feet first, would be significantly stronger than the pull on their head because their feet are closer to the center. This difference in gravitational force would stretch them out vertically while squeezing them horizontally.
Ouch.
This process is vividly, if gruesomely, nicknamed spaghettification. They would be torn apart into a stream of atoms before reaching the singularity at the center.
The singularity. What happens there?
Inside the black hole, within the event horizon, the singularity theorems, developed by Penrose and Hawking, showed that general relativity predicts the inevitable formation of a singularity, a point, or possibly a ring if the black hole is rotating, of infinite density and infinite space-time curvature. Here, space-time itself comes to an end. For the infalling astronaut, it represents an end of time.
Another place where physics breaks down.
Exactly. This breakdown led Penrose and Hawking to propose the cosmic censorship hypothesis. The idea is that singularities produced by gravitational collapse are always decently hidden from outside observers by being clothed within an event horizon. Nature prevents us from seeing the naked singularity where physics goes haywire.
God abhors a naked singularity, as Hawking put it.
That's the paraphrase. He even famously made a bet with physicists Kip Thorne and John Preskill about whether naked singularities could exist. Hawking conceded the bet later on a technicality involving specific theoretical scenarios, but claimed moral victory because the types of naked singularities found in those scenarios seemed unstable and unlikely to occur in reality.
Huh. Okay, so black holes trap everything, hide a singularity. What else do we know about them? What defines a black hole?
Remarkably little, actually. This leads to another famous finding called the no-hair theorem. It was proven through the work of several physicists, including Werner Israel, Roy Kerr, Brandon Carter, Hawking himself, and David Robinson.
No hair. What does that mean?
It means that once a black hole forms and settles down into a stable state, after swallowing matter or merging with another black hole, it loses almost all information about the object that originally collapsed to form it. The final black hole state is characterized only by three properties: its total mass, its total angular momentum, how fast it's spinning, and its electric charge, though astrophysical black holes are expected to have negligible charge.
Just mass, spin, and charge. That's it.
That's it. All other details, what the original star was made of, its magnetic field structure, the bumps and wiggles on its surface, all that hair is radiated away or swallowed, lost behind the event horizon. A black hole has no hair. This makes black holes incredibly simple objects from a theoretical point of view, despite their extreme nature.
For a long time, black holes were just theoretical curiosities, weren't they? Did we find any evidence?
Yes, for decades they were purely theoretical. But starting in the 1960s and 70s, observational evidence began to accumulate. One key piece came from observing quasars.
Quasars, those super bright objects far away.
Exactly. Quasars are incredibly luminous objects seen in the centers of very distant galaxies. Their energy output is enormous, far exceeding entire galaxies. The only plausible explanation for this energy is matter falling into supermassive black holes residing at the centers of these galaxies. As gas spirals into the black hole, it forms an accretion disk, heats up to millions of degrees due to friction, and radiates intensely before crossing the event horizon.
Supermassive black holes. How massive?
Millions or even billions of times the mass of our sun. Observations suggest that most large galaxies, including our own Milky Way, harbor a supermassive black hole at their center. The one in the galaxy M87, famously imaged directly in 2019, is estimated to be over 6 billion solar masses.
6 billion. Wow. What about smaller black holes?
Finding stellar mass black holes formed from the collapse of individual massive stars is harder, as they don't emit light themselves. The best evidence comes from binary star systems. If a visible star is seen orbiting an unseen companion that is too massive to be a neutron star, above that 2-3 solar mass limit, and if X-rays are detected, suggesting gas is being pulled from the visible star onto the companion, forming a hot accretion disk, then the unseen companion is a strong black hole candidate. Cygnus X1 was the first such candidate identified in the 1970s.
So the evidence is pretty strong now.
Very strong. We've also detected gravitational waves from merging pairs of black holes using detectors like LIGO and Virgo, directly confirming their existence and properties predicted by general relativity.
And you mentioned primordial black holes, tiny ones.
Yes, besides these astrophysical black holes formed from stars or galactic centers, there's also the intriguing theoretical possibility of primordial black holes. These wouldn't have formed from stellar collapse, but could have been created in the extremely dense and chaotic conditions of the very early universe just after the Big Bang from the collapse of overly dense regions.
How big would they be?
They could potentially span a huge range of masses, from much less than a gram up to thousands of solar masses. Ones with the mass of a mountain, for instance, would be smaller than a proton. Detecting these, if they exist, is a major challenge.
Okay, so black holes exist. They have event horizons, singularities, no hair. But then comes the ultimate paradox, right, where quantum mechanics crashes the party.
Exactly. The biggest twist in the story, and where Stephen Hawking made his most profound contribution, black holes aren't completely black.
Hawking radiation.
Hawking radiation. In 1974, Hawking, using the principles of quantum field theory in the curved space-time background near a black hole's event horizon, made the startling discovery that black holes should spontaneously emit particles. They should radiate thermal energy like a hot object.
But how? If nothing can escape the event horizon.
It's a subtle quantum effect. It defied their very definition and was met with, as Hawking described it, general incredulity at first. It seemed to violate the fundamental principle of black holes.
So what's the mechanism? How does it work?
It arises from applying quantum mechanics to the empty space near the horizon. Quantum mechanics tells us that empty space, the vacuum, isn't truly empty. It's actually teeming with activity. Pairs of virtual particles and antiparticles constantly popping into existence, flying apart briefly, and then coming back together and annihilating each other, all within the limits allowed by the uncertainty principle.
Virtual particle pairs.
Now, consider what happens right near the event horizon of a black hole. It's possible for one member of a virtual particle-antiparticle pair to fall across the event horizon into the black hole, while its partner escapes to infinity.
So one falls in, one escapes?
Yes. The particle that falls in can be thought of as having negative energy relative to an observer at infinity. Because gravity is so strong, it effectively borrows energy from the black hole. To conserve energy overall, the particle that escapes must carry away positive energy.
So energy escapes the black hole.
To the distant observer, it looks exactly like the black hole has just emitted a real particle with positive energy. This stream of escaping particles constitutes the Hawking radiation. It's a thermal radiation, meaning it has a temperature.
Black holes have a temperature.
According to Hawking's calculation, yes. And intriguingly, the temperature is inversely proportional to the black hole's mass. Smaller black holes are hotter and radiate more intensely. Larger black holes are colder and radiate very slowly.
So a solar mass black hole wouldn't radiate much.
Extremely little. Its temperature would be only a tiny fraction of a degree above absolute zero, far colder than the cosmic microwave background radiation. It would actually absorb more energy from the CMB than it emits. But a tiny primordial black hole, say with the mass of a mountain, could be quite hot and radiate significantly.
And what happens as it radiates? It's losing energy.
And since energy is equivalent to mass, as the black hole radiates, it loses mass. As it loses mass, it gets smaller. As it gets smaller, its temperature increases, and it radiates even faster.
A runaway process.
Yes. It leads to the astonishing conclusion that black holes are not eternal prisons. They eventually evaporate completely. For astrophysical black holes, this process takes an unimaginably long time, far longer than the current age of the universe. But a small primordial black hole could potentially evaporate entirely within the age of the universe, ending its life in a tremendous final burst of high-energy radiation, equivalent to, as Hawking calculated, millions of hydrogen bombs.
Oh, so the astronaut who falls in, they eventually get recycled.
In a sense, yes. Their mass energy eventually returns to the universe in the form of this thermal Hawking radiation. But importantly, the radiation is thermal, meaning it appears random and carries very little information about what fell into the black hole originally. This leads to the profound black hole information paradox. What happens to the information content of objects that fall into a black hole when it evaporates? Does it get destroyed, violating a key principle of quantum mechanics? Or does it somehow get encoded in the outgoing radiation in a subtle way? This is still a major area of research and debate.
And Hawking radiation connects to thermodynamics, entropy.
Yes, beautifully. The second law of thermodynamics states that the total entropy or disorder of a closed system always increases over time. Black holes seem to violate this. If you throw something with entropy, like a box of gas, into a black hole, its entropy seems to disappear from the universe, decreasing the total.
But Hawking radiation fixes this.
It does. Jacob Bekenstein had earlier proposed that black holes themselves should have an entropy proportionally to the area of their event horizon. Hawking's work showed that when a black hole emits radiation, it loses mass and its horizon area, and thus its Bekenstein entropy decreases. However, the entropy carried away by the emitted thermal radiation is actually greater than the decrease in the black hole's entropy. So the total entropy of the universe, black hole entropy plus radiation entropy, still increases, satisfying the second law.
Incredible. A deep connection between gravity, quantum mechanics, and thermodynamics.
Exactly. Hawking radiation was the first major prediction that relied crucially on combining both general relativity, to describe the curved spacetime, and quantum mechanics, to describe the particle behavior. It powerfully highlighted the urgent need for a complete theory of quantum gravity that could fully unify these two pillars of modern physics and resolve questions like the information paradox and the nature of singularities.
Okay, we've talked about time being relative, time ending inside black holes. But there's a more everyday mystery about time, isn't there? Something we experience constantly.
Indeed. Why does time seem to flow in only one direction?
Right. Why do we remember the past, but not the future? Why do cups shatter but never spontaneously reassemble themselves from the pieces? Why does disorder always seem to increase?
This leads us to the concept of the arrows of time. Why does time have a definite directionality in our experience, even though the fundamental laws of physics, for the most part, seem to work just as well forwards as backwards?
Most laws are time-symmetric.
Most of the fundamental laws governing particle interactions, like electromagnetism, gravity, the strong force, appear to be time-symmetric. If you recorded a process governed only by these laws and played the recording backward, it would still depict a physically possible process. For example, two billiard balls colliding looks plausible forwards or backwards.
But you mentioned the weak force violates time symmetry.
Yes, those subtle T violations associated with CP violation in the weak force do exist. They mean the universe would develop slightly differently if time ran backward. But these microscopic violations seem far too small to explain the overwhelming macroscopic arrow of time we observe in everyday life, the tendency for things to wear out, break down, become more disordered.
So where does that microscopic arrow come from? Hawking identifies 3 distinct arrows of time, right?
Yes, it's useful to distinguish between 3 arrows. 1, the thermodynamic arrow of time. This is the direction in which disorder, or entropy, increases. It's defined by the second law of thermodynamics. Things tend to go from ordered states to disordered states simply because there are vastly more possible disordered arrangements than ordered ones. A broken cup is a more probable state than an assembled one. 2, the psychological arrow of time. This is the direction in which we feel time passes. It's the direction in which we accumulate memories, remember the past, but cannot know the future. 3, the cosmological arrow of time. This is the direction in time in which the universe is expanding rather than contracting.
And are these arrows related? Why do they all point in the same direction for us?
Hawking argues compellingly that the psychological arrow is fundamentally determined by, or at least aligned with, the thermodynamic arrow.
How so? Our sense of time comes from entropy.
Think about how our brains work, or how a computer stores information. To form a memory or store a bit of data requires moving from a relatively disordered state to a more ordered state within the brain or computer chip. However, the physical process of doing this, running the brain cells, powering the computer, inevitably requires energy. And using energy always dissipates some of it as waste heat, which increases the overall disorder entropy of the surrounding environment.
So creating order locally increases disorder globally.
Exactly. And the increase in the universe's total disorder is always greater than the local increase in order involved in forming the memory. Therefore, we remember things in the direction in which the total entropy of the universe is increasing. Our psychological arrow aligns with the thermodynamic arrow. We remember the past because the past corresponds to a lower entropy state of the universe than the future.
That's a fascinating connection. Our subjective experience of time linked to a fundamental law of physics. But that just pushes the question back, doesn't it? Why does the thermodynamic arrow exist at all? Why did the universe start in such a highly ordered, low-entropy state in the first place, allowing for entropy to increase consistently ever since?
That is the crucial question. Why the low entropy beginning? Classically, relying just on general relativity, the Big Bang singularity was simply a boundary condition where the laws broke down. Science couldn't say why the initial state was so ordered, it just seemed to be a necessary input to get the universe we see.
But quantum gravity offers a different perspective.
Yes, this is where quantum gravity, and specifically the no-boundary proposal developed by Stephen Hawking and James Hartle, offers a potentially profound new insight.
The no-boundary proposal, what's the idea there?
The idea arises when trying to combine general relativity with quantum mechanics using Richard Feynman's sum over histories approach. This involves considering all possible space-time geometries that could connect the past to the present. To avoid technical difficulties with infinities, Hartle and Hawking proposed performing this sum using imaginary time.
Imaginary time, like the square root of -1.
Exactly, time measured using imaginary numbers instead of real numbers. Mathematically, using imaginary time has the effect of blurring the distinction between time and space. In this framework, they found it was possible for the universe to be finite in extent, but have no boundaries, no edges, no beginning or ending points, no singularities where the laws break down.
Finite but unbounded, like the surface of the Earth.
Precisely like the surface of the Earth. The surface of the Earth is finite in area, but it has no edge or boundary. You can travel anywhere on it without falling off. Hartle and Hawking proposed that the universe, in imaginary time, might be like that a four-dimensional analog of the Earth's surface. The beginning of the universe, analogous to the North Pole, wouldn't be a singularity, but just a smooth point in space-time.
So no sharp beginning, no singularity.
In this no-boundary picture, there's no need for an initial singularity or an edge where you have to specify special initial conditions. The universe would simply be E. The boundary condition of the universe is that it has no boundary.
What does that imply about the initial state?
It implies that the universe must have started in a very specific state, as smooth and ordered as possible, consistent with the uncertainty principle. It would begin with the minimum possible non-uniformity allowed by quantum fluctuations. It naturally starts in a low entropy state.
So the no-boundary proposal automatically gives you the ordered beginning needed for the thermodynamic arrow of time.
That's the beautiful implication. It provides a potential physical reason for why the universe started off smooth and ordered, setting the stage for entropy to increase and for the thermodynamic arrow to exist. It removes the need to simply postulate the low entropy initial state. It could be a consequence of the fundamental nature of quantum gravity.
And this smooth beginning connects to inflation.
Yes, this very smooth, ordered initial state predicted by the no-boundary proposal fits perfectly with the theory of cosmic inflation. Inflation proposes that the universe underwent a period of extremely rapid exponential expansion in the first tiny fraction of a second. This would take the initially smooth state and stretch it out to enormous scales, explaining the large-scale uniformity we observe today. Furthermore, inflation would amplify the tiny quantum fluctuations present in that initial state due to the uncertainty principle into slightly larger density variations.
And those
became the seeds for structure formation. The slightly denser regions eventually attracted more matter through gravity, collapsing to form the galaxies, stars, and planets we see today. The pattern of these initial fluctuations, predicted by inflation and the no-boundary condition, matches incredibly well with the detailed maps of the cosmic microwave background radiation made by satellites like COBE, WMAP, and Planck.
So observation seems to support this picture.
The CMB observations provide strong circumstantial evidence supporting inflation, which in turn fits well with the kind of smooth beginning suggested by the no-boundary proposal. It provides a coherent story linking quantum gravity, the initial state, inflation, and the large-scale structure of the universe, and explains why the thermodynamic arrow exists.
This seems to lead into the anthropic principle. How does that fit in?
Yes, the anthropic principle comes into play when we start asking why the universe has the specific properties it does, properties that seem remarkably well suited for the existence of life, including intelligent observers like ourselves.
What are the different versions of this principle?
There are essentially two main versions. The weak anthropic principle, WAP. This is less controversial. It basically states that in a universe that is vast enough, either in space or time, or perhaps containing many domains with different properties, the conditions necessary for the development of intelligent life will only be met in certain limited regions or epochs. Therefore, intelligent beings like us should not be surprised to find ourselves observing a universe, or a part of it, that possesses the characteristics required for our existence. It's a kind of selection effect.
Like we wouldn't be here to observe it if the conditions weren't right.
Exactly. For example, WAP explains why we find ourselves living now, about 14 billion years after the Big Bang. It takes billions of years for stars to form, create heavy elements through fusion, explode as supernovas to distribute those elements, and then for new stars and planets, like our Sun and Earth, to form from that enriched material, and finally for life to evolve. We simply couldn't exist much earlier in the universe's history.
Okay, that seems reasonable. What about the strong anthropic principle?
The strong anthropic principle, SAP, is more speculative and controversial. It suggests that the universe, or perhaps the fundamental laws of physics themselves, must have properties that allow life to develop within it at some stage. One interpretation of SAP is that there might exist many different universes, perhaps infinitely many, each with different initial conditions or even different fundamental constants and laws. Part of a multiverse.
A multiverse. Wow.
In this scenario, only in those rare universes where the laws and constants happen to fall within the very narrow range required for complexity and life to emerge would observers like us evolve. We find ourselves in such a universe because the others are sterile and have no one to observe them.
So it explains the apparent fine-tuning of the universe.
Yes. Proponents argue it addresses the observation that many fundamental physical constants like the strength of the forces, the masses of elementary particles, the cosmological constant seem remarkably fine-tuned. If they were even slightly different, stars might not form, or chemistry wouldn't work, or the universe might have recollapsed immediately or expanded too quickly for structures to form. Life as we know it would be impossible. SAP suggests this isn't incredible luck or design, but simply that we could only exist in a universe with such fine-tuning.
What are the problems with the strong anthropic principle?
Well, the main objections are, first, in what scientific sense do these other universes exist if we can never observe or interact with them? It risks becoming unfalsifiable metaphysics rather than testable science. Second, it seems to somewhat reinstate humanity, or life, to a special central place in the cosmos, which goes against the general trend of scientific discoveries since Copernicus and Galileo, the principle of mediocrity.
Does the no-boundary proposal help here?
It might. If the no-boundary proposal, combined with inflation, suggests that many different initial quantum fluctuations could have evolved into a universe broadly similar to ours, then perhaps the degree of fine-tuning required isn't as extreme as it first appears. It might reduce the need to invoke either a deliberate designer or a vast multiverse to explain why our universe is habitable. The laws themselves, derived from quantum gravity, might strongly favor universes like ours.
Okay, one last puzzle about the arrows of time. Why do the thermodynamic arrow, increasing disorder, and the cosmological arrow, universe expanding, point in the same direction?
Right. Why does disorder increase as the universe expands? Could it be the other way around? If the universe eventually stops expanding and starts to contract towards a big crunch, as the no-boundary proposal, when interpreted in real time, might suggest.
Would the thermodynamic arrow reverse? Would entropy start decreasing?
That's a fascinating thought experiment.
Right.
Would broken cups start reassembling? Would we remember the future, like tomorrow's stock prices, instead of the past?
Sounds like a great premise for science fiction. But is it plausible?
Probably not. Hawking argues that intelligent life, as we understand it, requires a strong thermodynamic arrow pointing in the same direction as this subjective psychological arrow. We need to operate by consuming ordered energy, like food, and converting it into disordered energy, like heat, to think, live, and record memories.
So life needs increasing entropy.
Yes. And he suggests that the conditions in a contracting phase of the universe would likely be very different from the expanding phase. The contracting phase would likely be highly disordered and chaotic, unsuitable for the stable evolution of complex structures like stars, planets, and intelligent life. There might not be a strong thermodynamic arrow in the required direction.
So the weak anthropic principle comes back again.
Exactly. We observed the thermodynamic and cosmological arrows pointing in the same direction, disorder increasing while the universe expands, because intelligent life capable of asking this question can only evolve and exist during the expanding phase, when conditions are right, sufficiently ordered initially, and the necessary thermodynamic arrow is present.
So it's not that expansion causes disorder to increase.
No, it's more subtle. The no boundary condition implies the universe starts ordered. Entropy increases according to the second law. This happens during the expanding phase. And intelligent life can only exist under these conditions. So we observe the eras align because that's the only epoch compatible with our own existence. Our very being is tied to this specific cosmic era and its directional flow of time.
This brings us really to the ultimate goal, the holy grail of theoretical physics. A complete unified theory of everything.
The ultimate quest.
Einstein famously spent most of his later years searching for this, trying to unify gravity with electromagnetism, didn't he? He wanted to find the equations that described everything, to know the mind of God, as he put it.
He did. He chased this dream relentlessly, but ultimately unsuccessfully. The main reason was that the necessary pieces just weren't yet in place. The weak and strong nuclear forces weren't well understood then. And crucially, Einstein never fully accepted quantum mechanics, despite his own fundamental contributions to its early development, like explaining the photoelectric effect.
He didn't like the randomness, the probabilities.
He famously objected to its probabilistic nature, the uncertainty. He couldn't believe that the fundamental description of reality involved chance. But quantum mechanics turned out to be essential. You can't build a unified theory without it.
Have there been times when physicists thought they were close to the end?
Oh yes, several false dawns, as Hawking calls them. Times when it seemed like the fundamental laws were nearly complete. For example, around the turn of the 20th century, before relativity and quantum mechanics. And again, Max Born in 1928, after Paul Dirac formulated his relativistic equation for the electron, which predicted antimatter, supposedly claimed that physics as then known would be over in 6 months.
Didn't quite work out that way.
Not at all. The discovery of the neutron, the nuclear forces, the zoo of new particles, it showed there was much more complexity. The core challenge in achieving unification today remains the fundamental incompatibility between our two great theories, general relativity and quantum mechanics.
General relativity for the large scale, gravity.
Mm-hmm.
Quantum mechanics for the small scale, the other forces, and they don't play well together.
They don't. General relativity is a classical theory, describing a smooth, deterministic space-time. Quantum mechanics is inherently probabilistic and fuzzy, dealing with discrete quanta and uncertainty. Trying to combine them directly leads to mathematical disasters.
Like the infinities you mentioned.
Exactly. The uncertainty principle from quantum mechanics is a huge hurdle. It implies that even empty space isn't truly empty. It's filled with these virtual particle-antiparticle pairs constantly popping into and out of existence. These pairs possess energy, and by E Plommonot, they should therefore have mass.
Infinite energy.
When you try to calculate the total energy density of these vacuum fluctuations using standard quantum field theory, the answer comes out infinite. And according to general relativity, infinite energy density would mean infinite mass, which should warp space-time infinitely, curving the universe up into an infinitely small size.
Which clearly hasn't happened.
Clearly not. So this infinite result signals a deep inconsistency when you try to naively combine quantum mechanics and general relativity. We need a new framework, a theory of quantum gravity that resolves these infinities.
What attempts have been made? You mentioned supergravity.
Yes, one major approach in the 1970s was supergravity. This theory attempted to unify general relativity's graviton, spin 2, with other particles having different spins, spin fan 1, spin 32, through a new kind of symmetry called supersymmetry.
Supersymmetry, what's that?
Supersymmetry proposes a fundamental relationship between the two basic classes of particles. Fermions, matter particles, spin, and bosons, force carriers, integer spin. It postulates that every known particle has an undiscovered superpartner with a spin differing by half. So electrons, fermions, would have selectrons, bosons, photons, bosons would have photinos, fermions, and so on.
And how would that help with the infinities?
The hope was that the infinite contributions to the vacuum energy from the virtual boson loops would be exactly canceled out by infinite contributions with the opposite sign from the virtual fermion loops, thanks to this supersymmetry. It seemed very elegant.
Did it work?
It helped, but ultimately, supergravity theories still seem plagued by intractable infinities when calculations were pushed far enough. The mathematics involved became incredibly complex, making it very difficult to prove whether all the infinities truly canceled, and crucially, none of these predicted superpartner particles have ever been discovered experimentally, despite extensive searches at particle accelerators like the LHC.
So supergravity didn't quite crack it. What came next?
Then, around 1984, there was a remarkable change of opinion, as Hawking describes it, towards a different, even more radical approach. String theory.
String theory. What's the basic idea there?
Instead of viewing the fundamental constituents of nature as zero-dimensional point particles, string theory proposes that the truly fundamental objects are tiny, one-dimensional vibrating filaments or strings. They can be open-ended or closed loops.
So everything is made of tiny strings.
Yes. And just like a violin string can vibrate at different frequencies, producing different musical notes, these fundamental strings can vibrate in different patterns or modes. And according to string theory, these different vibrational modes correspond to what we perceive as different elementary particles, electrons, quarks, photons, gravitons. They are all just different notes played by the same fundamental string.
It's a very different picture.
It's a radical departure. And interactions between particles, which in point particle theories are represented by lines meeting at a point, in string theory become strings joining together or splitting apart, like the joining or splitting of pipes. String theory is rather like plumbing, as Hawking humorously put it.
Does string theory include gravity?
Yes. One of the most exciting aspects of string theory is that it naturally incorporates a particle with the properties of the graviton, the carrier of the gravitational force. Unlike previous attempts, gravity isn't just added in, it emerges necessarily from the theory itself. And crucially, the calculations in string theory seem to avoid the problematic infinities that plagued earlier attempts to combine gravity and quantum mechanics. The fuzziness of the string, compared to a point particle, smooths out the interactions at very small distances.
That sounds promising. Any catches?
Oh, there are catches. Big ones. One is that string theories are only mathematically consistent if spacetime has more dimensions than the 4, 3 space plus 1 time that we experience.
More dimensions. How many?
Typically, string theories require spacetime to have 10 dimensions, 9 space plus 1 time. Some earlier versions even required 26.
10 dimensions.
Yeah.
But where are the extra 6 spatial dimensions? We certainly don't see them.
That's the big question. The standard explanation within string theory is that these extra dimensions are compactified. They are curled up into incredibly tiny, complex shapes, perhaps on the scale of the Planck length, about 1035 meters, far too small for us to perceive directly.
Curled up? Like how?
Imagine a garden hose. From far away, it looks like a one-dimensional line, but if you look very closely, you see it has a second dimension, its circumference, curled up around the length. The idea is that at every point in our familiar 3 large spatial dimensions, there's also a tiny, curled-up 6-dimensional space.
Wow, that's hard to visualize.
It is. And there seem to be a vast number of ways these extra dimensions could be curled up, estimated perhaps as high as 100 and 500 possibilities, each potentially leading to a different set of effective physical laws and constants in our large dimensions. This landscape of possibilities is a major challenge for string theory's predictive power.
So how do we know which curled-up shape is the right one for our universe?
We don't, currently. This is where the anthropic principle sometimes reappears. Maybe only a tiny fraction of these possible compactifications lead to universes capable of supporting life, and we naturally find ourselves in one of those.
The anthropic principle again.
Yes. It's also invoked to explain why we have exactly 3 large spatial dimensions. String theory itself doesn't necessarily dictate this, but arguments suggest that life as we know it might only be possible in 3 plus 1 dimensions. For instance, in universes with more than 3 large spatial dimensions, gravity would fall off faster with distance, making stable planetary orbits potentially impossible. Atoms might also be unstable. So perhaps we observe 3 large dimensions simply because that's the only dimensionality compatible with observers existing.
String theory sounds incredibly complex and maybe untestable.
Yeah.
Is it still the leading candidate?
It remains a very active area of research and arguably still the most promising framework we have for unifying gravity and quantum mechanics. There have been significant developments like the discovery of duality, surprising mathematical connections suggesting that the 5 different consistent superstring theories developed in the 1980s, plus supergravity, might all be different approximations or limiting cases of a single, deeper underlying theory, tentatively called M theory, where M might stand for membrane, magic, mystery, or mother.
M theory. So the quest continues.
The quest definitely continues. Finding this complete unified theory, whether it's M theory or something else, remains the ultimate goal.
And if we found it, what would that mean?
Hawking believed that discovering a complete unified theory, if successful, would be the ultimate triumph of human reason. It would represent a complete understanding of the fundamental laws that govern the universe. It wouldn't just be for specialists. He hoped it could eventually be understood in broad principle by everyone.
So everyone could understand the universe.
In principle, yes. He envisioned a time when we could all take part in the discussion of the question of why it is that we and the universe exist. Knowing the fundamental laws would be the starting point for addressing these ultimate philosophical questions from a scientific perspective.
But even if we found this ultimate theory, could we then predict everything? Would free will be an illusion?
Hawking argues no for 2 main reasons. First, the inherent unpredictability of quantum mechanics enshrined in the uncertainty principle would still remain. We could only predict probabilities, not definite outcomes, at the micro level.
Okay, quantum fuzziness remains.
Second, even if we knew the fundamental equations perfectly, solving them for any complex, realistic situation would be computationally impossible in practice. Think about it. We already know the fundamental laws governing chemistry and biology reasonably well, but we are nowhere near being able to predict human behavior, for example, just by solving equations for the atoms in our brains. The complexity is overwhelming.
So emergence and complexity are still real challenges.
Absolutely. A complete unified theory would just be the first step. The enormous intellectual challenge of developing approximation methods and understanding the emergent behavior of complex systems governed by those laws would remain.
So Einstein's question. How much choice did God have in constructing the universe? What's the potential answer now?
Well, if the no-boundary proposal is correct, it suggests God, or whatever underlying principle you prefer, had no freedom at all in choosing the initial conditions for the universe. Those would be fixed by the requirement of having no boundary.
So the choice is only in the laws themselves.
Potentially, yes. The freedom might only lie in choosing the fundamental laws, but even that choice might be severely limited or perhaps non-existent. It's possible that there is only one, or maybe a very small number, of complete, self-consistent, unified theories that are mathematically possible and also allow for the existence of structures as complex as human beings, capable of investigating the laws of the universe that govern them.
So the universe might be the way it is because it's the only possible way.
That's the tantalizing possibility, that the ultimate theory is unique, constrained by mathematical consistency, and perhaps the requirement that allows observers to emerge. Hashtag outro.
What a journey, seriously. From Aristotle's turtles and Ptolemy's perfect celestial circles, all the way to the truly mind-bending concepts of warped space-time, quantum fluctuations, black holes evaporating, and maybe even a universe without a beginning or end. What we've unpacked today really fundamentally reshapes our understanding of reality.
It really does. We've seen how science builds upon itself step by step, often through challenging, cherished assumptions. We've seen how crucial observation is and how even the greatest minds can be surprised, maybe even humbled, by the universe's inherent elegance and, well, its sheer strangeness and complexity.
Yeah, elegant and strange at the same time.
And this pursuit of a unified theory, this quest for a single explanation for everything from quarks to quasars, is perhaps the most profound intellectual adventure humanity has ever undertaken. It drives us to probe ever deeper layers of reality.
It's a story of constant discovery, isn't it? Where even seemingly empty space is actually teeming with quantum activity, where time itself becomes a personal journey, not a universal metronome, and where our very existence might be a subtle consequence of broken symmetries and finely tuned cosmic laws. This deep dive into Hawking's work is a powerful reminder that the universe is not only stranger than we imagine,
but stranger than we can imagine, as J.B.S. Haldane famously said.
Exactly.
Indeed. And as we continue this quest for understanding, it's worth remembering that even if we were to discover that ultimate theory, that final set of equations, our journey wouldn't end there. Not by a long shot.
Why not?
Because the real challenge would then be in making sense of it, in translating those fundamental laws into a coherent understanding of the incredibly complex world around us, from the behavior of materials to the workings of life, to consciousness itself, and understanding our own place within that grand cosmic tapestry.
So if the universe is truly self-contained, as the no-boundary proposal suggests, without boundary, without a singular beginning or end, and if there's ultimately only one unique, self-consistent set of laws that allows for observers like us, then the question for you, the listener, perhaps becomes, what does it mean for us to truly know the mind of God if that mind, in the end, had no choice but to follow its own perfect singular logic?